Hello and welcome to today's PIR Live Event Webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. If you're joining us live, please remember that you can ask questions anytime throughout the webinar by clicking Q&A near the bottom center of your screen and typing in your question for us. If you do see a question that was asked by someone else and you're also wondering about that question, please click the thumbs up icon that you'll find either beside or below that question. And that is a way to upvote that question. So to let us know that that's maybe something we should prioritize and answer because multiple classrooms are wondering about that answer. And if possible, let us know where that question is coming from. It could be a student's name, it could be teacher's name, a school name, maybe the city you're in, some sort of identifier so that when we ask that question, you know that it came from you. Today's guest is Francesco Tangorra. He is a professor of civil engineering technology at Algonquin College. Thank you so much for joining us. I will let you take it away.
Thank you so much, Stacey, and hello to everybody who's joining us across Canada and in the US. I'm going to take a moment to bring up my presentation. I'll chat with you for a little bit about structures in general with a little bit of detail, and then I'll also be available to answer some of the questions that you might have. I'll just take a moment to share my screen with you. There we go. There. Can you see my screen now? Excellent, thank you. Okay, so let's get started with this. I want to chat with you today a little bit about structures in general to give you a taste for what structures are and how to consider them. My name is Francesco and I'm here at Algonquin College in Ottawa, Ontario. I would like to start with maybe a little bit about me. My full name is Francesco Tangorra, and I've included for you a way to pronounce my name so that you're not worried about doing so incorrectly. I am currently a professor in civil engineering technology at Algonquin College in Ottawa, Ontario, Canada. I am also a professional engineer in the province of Ontario, which means that I'm licensed to provide engineering services in Ontario with some other requirements. My professional background before I joined the faculty at Algonquin College was as a structural engineer and a collapse investigator. So what that basically meant is that I helped buildings or companies ensure that their buildings stayed up. Also, whenever there were problems with a building and a building came down or there were damages to it, I assisted with the investigation and trying to find out why that happened to see if it could be fixed or repaired. Okay, let's get to the meat of today's chat. What are structures? I'd like to give you an idea of what structures are really for buildings in a way that would make sense to all of us. Structures in buildings are what bones and muscles are for us. So bones and muscles allow us as people, as humans, to stand up and be stable, to be strong enough to resist all forces that come on us, right? And they allow us also to move as needed. Well, structures do exactly this for buildings. Structures are the bones and muscles of buildings. So where bones are good with resisting forces that are in compression, and where muscles act in tension, the same thing is true for structures. So I would like to delve a little bit in more detail how that works for structures then, the bones and muscles of buildings. So structures are basically what keep buildings up. Structures are also what keep buildings safe and strong. It's not just important that your building stays up, it must also be safe for the people or other occupants that use it, and strong enough to resist everything that's going to be affecting that building. So across Canada right now, that includes wind, snow, rain, cold temperatures, warm temperatures, and anything else that you can think of. So understanding structures becomes very important, and that's a big part of what I do as an engineer. So I'd like to maybe delve a little deeper into what it means to understanding structures. It basically deals with sub-portions of engineering like structural analysis, that is, figuring out the forces in all the portions of a structure. It also means being comfortable with what's called material science, that is, knowing how a specific type of material will behave so that your building is safe. So if you choose to use concrete or steel or wood or adobe or snow and ice for your building, that your building does exactly what you expect out of it. Finally, I would round that up also with a good grasp of math. And that's because mathematics, is the language that we use to be able to describe what happens to forces in nature and therefore how our buildings will behave. Now, you might think, and you'd be right in believing, that this can be fairly complex. But the question is, does it have to be complex and complicated? So I'd like you to consider the following. This is the Fourth Rail Bridge in Scotland. It was built over the span of about 7 years between 1882 and 1889. It's a fairly large bridge and it's beautiful to view. So this photo, I don't think, does it justice. When the structural engineers were asked to explain how this bridge worked, they didn't go into the complexities of the math involved with it. Instead, what they did is they used their bones and muscles to show it. And I'm going to show you exactly what I mean. This is a photo from 1887 showing the structural engineers that designed that bridge. And you can see how by using their arms and by using weights and bricks, they're mimicking exactly the shape of the bridge and exactly how it behaves. So you can see just by looking at them, you can tell where they're using their arms to hold things up. Their arms are being pulled on. That means they're in tension. Those metal rods that you see their arms holding, they're in compression. And by having those weights at the other end, they're able to balance everything out so they can hold that other gentleman in the middle. And this goes to show you that it doesn't have to be complicated analyzing a structure if you can grab an overall understanding of how the whole thing behaves. And we'll come back to this near the end of our quick chat. What I would like to do now, if you'll allow me, is to actually maybe take you on a trip, a virtual trip around the world in Canada, so that I can show you some of the amazing buildings we have. Oldest buildings, tallest buildings, longest bridges, and so on. So let's start with oldest buildings. What do you think the oldest building in Canada is? If you said the Viking houses in Newfoundland, you're right. So these have been dated back to about the year 1000. Now, I want to be clear, the Aboriginal people of Canada have been in Canada a lot longer than that. The only thing is that none of their buildings have survived or have yet to be discovered, and that comes with the nature of their culture. How about in the world? What do you think the oldest building in the world is? Well, it turns out to be the Barnenez Mound in France. It's been dated back to about 4800 BC. Most of its construction, as you can see, it's basically stone and rock. Now, this is important too. It's not as if there weren't civilizations and buildings that were there before 4800 BC. It just happens that those buildings likely did not survive or have not been discovered yet. I'm going to guess that some of you might have said that maybe the pyramids in Egypt might have been some of the oldest buildings in the world. And you would be close. They were from about 2650 BC. The reason I bring them up is because I want to share with you something that I only recently noticed or found out about them. This is the common view of the pyramids of Giza. So you get to see 3 pyramids in the middle of the desert, and then depending on the view, you can also see the Sphinx. Well, did you actually know that these pyramids are, in fact, quite close to the nearby city? So the view that you get to see is true, but not quite the full picture. They're actually very close to the nearby city. And in fact, if you were to look it up online, you would find a somewhat famous picture that actually shows a view of the pyramids through a storefront. I think it's a Pizza Hut storefront nearby. Okay, let's move on to tallest. What do you think the tallest structure in Canada is? If you said the CN Tower, you're right. At 553 meters from bottom to very top, it's the tallest structure in Canada. In fact, for the longest time, it was the tallest one in the world. It was completed in 1976. How about what is currently the tallest structure in the world? If you said the Burj Khalifa in Dubai, you are right. At 829.8 meters, this building is almost 1 kilometer tall. It was built over 5 years from 2004 to 2009, and it's truly breathtaking. You can see how with a structure this big, knowing how the material is going to behave, right? The concrete, the steel, it becomes very important. Okay, now for Canada, I showed you the CN Tower. It's not quite a building, right? People don't live there. So how about maybe we try to figure out what the tallest building in Canada is? This is a bit tougher. It happens to be the first Canadian place in Toronto. At 355 meters, it is the tallest building in Canada. So people live here, probably, work here for sure, and spend a lot of their time in this building. It was completed in 1975, and it's in Toronto, Ontario. Okay, now, do you know what the tallest building in the world is? Yes, we covered it just a moment ago. It is still the Burj Khalifa. So this is used for people living in there. There are shops. There is, I believe, a multi-story aquarium in it. It's just truly, truly amazing. We've looked at tall. How about long? Do you know or can you guess what the longest structure in the world is? If you guessed the Great Wall of China, you are correct. The Great Wall of China is incredible. It is estimated that its construction was started around 600 BC, and it continued for the next millennia or so. It measures, when all the parts are measured, over 21,000 kilometers. To put that into perspective, 21,000 kilometers is the equivalent of going from the Atlantic coast of Canada to the furthest point on the Pacific coast of Canada, and then back, and then almost back again. So it's truly, truly huge. Now, this is an incredible feat of construction. The question is, and I don't know if you know this, can you actually see the Great Wall of China from space? Well, I can tell you what I found out. I attended a lecture a few years ago by Canadian astronaut Chris Hadfield in Waterloo, Ontario. And he was asked exactly that question. Were you able to see the Great Wall of China from space? And his answer was no. And that's not because this is not such a huge, awesome structure. It's because its color makes it perfect for blending with the nearby environment. So it actually is very hard to pick out in space when he tried looking for it. Okay, Now, I couldn't find a similar type of structure in Canada, so what I did instead is I moved on to bridges. Do you know what the longest bridge is in Canada? If you said the Confederation Bridge, you're spot on. So this is a bridge that connects PEI to New Brunswick, and it was built over about 4 or 5 years, 1993, 1997. It measures almost 13 kilometers, and most of it is over open water. And that's truly amazing because that water tends to freeze over the winter months, which means that this bridge has to resist the forces of chunks of ice hitting its piers. Okay, how about in the world, the longest bridge in the world? Do you think it would be maybe twice this length? Try more than 10 times. The longest bridge in the world is the Danyang Kunshan Grand Bridge in China. It's almost 165 kilometers long. It is truly a marvel of engineering. So you can see how with something like this, it is important to make sure that the materials that are used behave the way you want them to, and that you can understand properly how the structure acts. So I now want to kind of circle back, if I could, to, let's see. There. Am I back on your screens? No? All right. Let me just make sure that I'm...
I see you right now in almost your screen. Oh, not now.
How about now?
Are you trying to share more slides?
No, I think I just want to be back on the screen now.
Oh, I can see you, yes.
Okay. All right. So at this point, then, I want to kind of circle back to what we were talking about when it comes to structural analysis and figuring out how structures behave. Like you saw, those engineers who just used their arms to show how that bridge behaved, that was a simple way of doing it. How could you do it if you were interested in doing the same? I mean, you might not have the mathematical level because you haven't been to university or college yet. Well, I'm going to propose to you something that some of my students have done, for example, which is, first of all, dream of it. If you can dream it, you can work your way towards it. Second of all, if you can build it, right? If you can build a model of it, you can try out to see how it behaves. This here, for example, is a bridge made out of popsicle sticks. And what students have done, they said, how is it going to behave? I'm not going to build an entire full-size bridge. I'll do something like this first. You can see here where it's cracked under the testing that they did on it to find out how it would behave in real life. You can even get really sophisticated to find out, say, how a suspension bridge like the Brooklyn Bridge or the Golden Gate Bridge would behave. And what I have here is an example of another bridge that some of my students behaved. So this one here, I hope you can see, is not actually meant to necessarily be tested, but to figure out the kind of shapes and locations of where you would put cables and chains and beams. And this could be also the kind of setup that you can put in a wind tunnel to find out how this bridge would behave, say, under wind. All of this is to basically say that playing around, being curious, and trying things out is a great way to get things started, especially until you develop those, say, math levels or science levels that you're looking for. It is truly amazing, and that's the point of progress. If you can dream it, you can make it happen. I think I'm going to stop there, just in the event that there are some questions to answer, but I want to thank you so much for your time, for listening to me.
Well, thank you for taking us on such a around the world tour of structures to see what has been done so far and to discuss maybe why it was done in that fashion. So we do have a few questions already. I am sure there will be more. If you are thinking of a question and you're with us live, then just find your way to the Q&A button on the bottom middle of your screen. And don't forget to let us know who the question is coming from, either a student's name, a teacher's name, a city, something that will identify where that question is coming from. So to start off, we have a question from Ms. Schutz's class, wondering if when you say the structure, do you mean the foundation? Are those equivalent terms?
That is a very good question. So the foundations are actually part of the structure. And if we want to use a human body analogy, that would correspond to, say, our feet and ankles. So it's the part of the overall structures, a structure that ensures that that building is properly resting on the soil below it or whatever surface it's sitting on. And that's where the foundations come into play. They ensure that whatever building or structure you have is properly supported by the soil below it. So that's an excellent question.
And our next question is from the grade 3s at Gladys Spears. How do bridges not fall down? And maybe here I'm going to elaborate a little bit, maybe what kind of forces might make them fall down, and how do we create something stable that will withstand those forces?
Great. That's a really good question. And I think what I'll do is I'm just going to reach over to the model of a bridge that I have here, because that will help. So to ensure that a bridge doesn't fall down, first of all, you want to make sure that whatever supports that bridge has that go all the way down to the ground or the riverbed are strong enough, right? These here need to be strong enough to support whatever weight of the bridge is attached to it. Secondly, whatever material is connecting to the towers or the piers, whether it be cables or beams, they also have to be strong enough so that they can resist, say, the weight of people walking across it or vehicles driving across it. Then you also have to make sure that this bridge is strong enough to resist nature. So that includes wind or rain or ice and snow or all of those things together, right? Because you can see how this bridge here is rocking, and you get that happening with real bridges too. So you have to make sure that all the parts that connect the deck and the piers or towers are strong enough on their own and strong enough together to resist nature and the people on them. So that's where material science comes into play, right? You have to pick the right materials to make sure this happens.
Excellent, thank you. Well, it looks like we have a few questions here that are coming from multiple sources, so maybe we'll get to those first. We have a question from Dylan, and this came from another classroom as well. What is the difference between a structure and a building?
That's a really, really good question. So the difference between a structure and a building, and I'm going to do the human analogy, is the same difference that there is between your skeleton and your muscles, which is the structure, and the whole person, which is the building. So the structure is there to ensure that the building stays up and is safe. The building encompasses everything. So it would not only encompass the structure, so say like your bones and muscles, but also whatever keeps that building warm, what allows you to get water in that building, the windows, the flooring, so the carpet and the electricity, right, to turn on the lights. All of that together makes a building because it's something that typically humans use, people use to live in or work in or have fun in. The structure only refers to that part of the building that makes sure it's safe, it stays up, and it's strong enough to resist all the forces you put on it.
Right. And next we have a question from Ms. Alexander's classroom, wondering how do engineers know how much weight a bridge will hold as they are building it?
That is a really good question. So it turns out that there are guidelines that are given out by the local governments. So in Canada, it would be by the provinces. I'm guessing in the United States, it would be from the states themselves that actually give specific guidelines for the expectation of how many cars or trucks or people will be in a bridge, depending on how wide that bridge is. That is, how many lanes it will have. And then on top of that, engineers also put a factor of safety. So just to put it in context, let's say the province or state says that you have to assume that bridge has to support 100 cars per hour. When an engineer then designs that bridge, he or she or they will then say, let's actually assume it's double that, just to be safe in the event that something else happens, like there is a traffic jam and also a lot of snow or lots of wind.
Right. Wonderful. So always sort of building on the safe side in case they need a little bit more strength to keep that stable.
Right. And that's because nature really doesn't wait for people to be done building whatever it is that they're putting together, right? Especially if you're living somewhere where you woke up to a lot of snow and cold, right? You don't know from one day to the next what the weather will be like.
Right. Well, our next question is from a grade 5-6 class, wondering, why are triangles used most often in bridge structures?
That is a terrific question. The nice thing about triangles is that they're the smallest number of sides. It's the shape with the smallest number of sides that is still stable. So that means you can always find 3 pieces of something, put them together, and get the most stable shape. It also uses the least amount of materials, and it's very efficient. Instead, if you get, say, a rectangle like this shape can tend to kind of squish, right? To make it stable again, you actually need a brace that goes from corner to corner to get a triangle again. It happens to be that triangles are the most simple and stable shape that you can get with the least number of sides.
Right. Well, that makes sense. Next we just have to find this question here. You mentioned material science as one of the things that comes into play when creating a structure or a whole building, bridge. That left the students at St. Julia's wondering, what are the common types of materials used to build the most stable and strong structures? And I have a feeling the answer is, it depends.
Yes, I agree. It does depend, but I can tell you the most common ones, but I'll start with why it depends. It depends a lot on where in the world you are. So say if you're building in North America, the common material used for homes, the kind of homes you and I live in, is typically wood. And that's because in North America, wood is plentiful. But if you move to places like Europe, there isn't much wood, so typically they'll go with concrete and steel. When it comes to structures, though, for big structures, typically the common materials are, in North America, steel, reinforced wood, and concrete blocks, so masonry blocks or bricks. For residential construction, smaller construction, is typically wood and steel with concrete for the basement. Okay, for super huge structures, they're really the ones that kind of make a statement. Usually you go with steel and reinforced concrete.
So lots of choices then when deciding to build something, anything.
Yes, certainly.
So changing the flavor of the question a little bit, we have a question coming from Sandhills in Kitchener, wondering, what is one collapsed structure that you have investigated?
Okay. So I'll tell you some of the types that I've investigated, because you may not be familiar with the details of the individual ones I might have investigated. I've been involved with, say, the collapse of roofs on homes from too much snow. And that has been happening recently, especially because we've been getting a lot more snow compared to, say, 50 years ago. So what ends up happening actually is that the province of Ontario, in this case, actually makes sure that new homes are built for more snow than, say, homes built 50 or 100 years ago. So that's an example. Another one would be, say, barns where you were storing equipment or material as a result of a tree falling on them. I've investigated collapses like that. Others included the fires, or say if a car got out of control on a road or a street in the middle of winter and ended up driving through someone's living room. So those are some examples of the kind of structures and investigations that I've done.
Interesting. And now we have a question from the grade 5s at Mohawk Gardens. And they're wondering, why have some structures like the Great Wall and the pyramids lasted so long while so many other structures have not?
That is a really good question. And a big answer to that is climate. And by that I mean what the climate is and the place where those structures or those buildings were created. So there are parts of the world, I'll pick, say, Egypt, for example, where the climate is relatively stable in terms of precipitation and humidity. So in Egypt, it's not common to see much snow at all during the winter, and it typically stays fairly warm throughout the year with a fairly constant level of humidity throughout the year after year, century after century. If you go to a place like Canada, you know that you can go from plus 40-degree weather, very hot and very humid in the summer, to minus 40 and lower temperatures in the winter, so very cold. And when that happens, you know also that there is salt and sand that's put on roads and so on, which attack structures. So that big change in temperature and humidity does have bad effects on structures, on buildings. And you don't really get to see that in some of these places where these huge, incredible structures still exist. The other one, too, is the material used. Some of these big structures were made with stones, right, and rocks, and they're really good at lasting for thousands of years. But if you go to a place where they were building in wood, like they did in North America, right, the Aboriginal people of Canada likely did a lot of their constructions, especially if they were mobile, with wood-type structures. Those don't last very long unless you make an effort to keep them. And that's not always worthwhile because it's easier to just build something new. So it's kind of a mix of what you make it out of and the local climate.
Right. Now, I see that we have many questions we haven't answered yet, but we are running out of time. So I do want to ask one of the questions we've received from multiple classrooms, including Ms. Orr's classroom. They were the first to ask this question pretty early on in your presentation, wondering what inspired you to become an engineer, a structural engineer.
Okay, I have to admit, and I'm realizing this now, it was basically starting as a young kid playing with Legos and figuring out how high I could go, and realizing that sometimes if I made my Lego really, really thin, my Lego tower really thin, it kind of got floppy and fell over. But if I started making it wider or turning Lego pieces around, it was a bit stiffer. And then starting to realize that outside of my town, outside of my countries, there were these amazing buildings, amazing bridges that were being built by other countries. And some of them were hundreds, if not thousands of years old. And I told myself, that's really awesome. I want to find out how that happened. And that kind of was the first step. And then I found out that to find out how that happened was becoming a civil engineer and a structural engineer. And it kind of told me what the path would have to be in terms of what I needed to learn and the topics I needed to study. I think passion and interest is probably top.
And we did have a question in there from Ms. Innocente's class wondering what your favorite toy as a kid was. So is it safe to assume it was Lego?
It was, yes.
Well, that is almost all the time we have. The last question I have for you is if you have any advice for any students who find this interesting and might want to pursue a similar career path.
Certainly. I think the top thing is interest and passion on your part, because you can't just make that up, right? The second one is continue with your studies of science and math, because they're important in then being able to translate and understand how nature behaves and how forces behave. But really the top one would have to be a passion and interest, because that will get you when, say, you're having a tough time in a test or so on.
That is all the time we have today. Thank you so much, Mr. Tangorra, for joining us today, for showing us and explaining to us such great examples and answering our questions.
Thank you for having me, everybody, and thank you so much.
So next week on PIR Live Event, we're learning about star formation. Information about this webinar, other webinars, and additional education programming is all available at pirweb.org. Thanks so much for tuning in, and have a great day, everyone.